Alright, let's dive into this problem. We are looking at a scenario with two gases, A and B, each in its own cylinder with a movable piston. They start at the same pressure. So here's the setup. We have gas A and gas B in separate cylinders. Both have pistons with radii A and RB respectively. An important detail is that the pressure is the same for both initially. Now we add the exact same amount of heat to both systems, and this happens reversibly under constant pressure. When we do that, the piston for gas A moves 16 centimeters and the piston for gas B moves 9 centimeters. They also tell us that the change in their internal energy is identical for both gases. Our goal is to find the ratio of the piston radii, that is Ra over Rb, and we have a few options to choose from. To tackle this, we start with a fundamental concept, the first law of thermodynamics. This law tells us that the heat we supply to a system, which we call Q, is used in two ways. It changes the system's internal energy, delta U, and the rest is used by the system to do work, W. So we can write this simply as Q equals delta U plus W. This will be our starting point for both gases. Next, let's think about the work done, especially in the case of a piston moving under constant pressure. The work done by the gas is equal to the pressure, P multiplied by the change in volume, delta V. Now, how does the change in volume relate to our piston? Well, the cylinder has a constant cross-sectional area. Let's call it A. When the piston moves a distance, delta x, the change in volume is simply that area, A multiplied by the distance delta x. Since the piston is circular, its area is given by pi times the radius squared pi r squared. Putting it all together, the work done, W, is equal to the pressure P times the area, A times the displacement delta x. So W equals P times pi r squared times delta x. Okay, let's apply these concepts to our two gases, A and B. Remember the first law, Q equals delta U plus delta, U plus W, and our work formula, W equals P times delta x. For gas A, the pressure is P, the displacement delta x A is 16 centimeters, and the radius is Ra. So the heat supplied to AQA equals the change in internal energy for A delta UA plus the work done by A, which is P times pi times Ra squared times 16. Similarly, for gas B, the pressure is also P. The displacement delta XB is 9 centimeters and the radius is RB. So the heat supplied to BQB equals the change in internal energy for B delta UB plus the work done by B, which is P times pi times RB squared times 9. Now we use the specific conditions given in the problem. We were told that an equal amount of heat is supplied to both systems, so QA equals QB. Let's just call this value Q. We were also told that the change in their internal energy is the same, so delta UA equals delta UB. Let's call this value delta U. Substituting these into our equations from the last step, for gas A we have Q equals delta U plus P times pi times Ra squared times 16. And for gas B we have Q equals delta U plus P times pi times Rb squared times 9. Since both of these equations are equal to the same value, Q, we can set them equal to each other. This gives us delta U plus P times pi times Ra squared times 16 equals delta U plus P times pi times Rb squared times 9. Alright, let's finish up by solving for the ratio Ra over Rb. We start with the equation shown here. Notice we have delta U on both sides, so we can cancel that term to simplify things. Then, since pressure P and pi are common factors on both sides and are not zero, we can cancel those as well. This leaves us with terms only involving Ra squared and Rb squared. Now to find the ratio Ra over Rb, we rearrange the equation to get the ratio of Ra squared over Rb squared on one side. Finally, we take the square root of both sides. Taking the square root of 9/16 gives us our final answer of 3/4 for the ratio Ra over Rb. And there we have it. The ratio of the piston radii Ra over Rb is 3/4. This matches option 3 from our choices. So the final answer is indeed 3/4.